Okay, so still now, previous day we have discussed the H parameter model, started the H parameter model discussion of the transistor. Okay, and in the H parameter model discussion, except the okay, this is the H parameter model, and I have discussed the parameter calculation. In terms of the parameter calculation, I have calculated the current gain and shows the how the current gain will look like. So this is the expression for the current gain, and also we have calculated the input resistance. So input resistance is, this is the expression for the input resistance after the simplification. Okay, so and next we have calculated the voltage gain. So voltage gain is also represented by this expression. So these are the three expression we have derived till now: voltage gain, input resistance, and the current gain. So next we will continue from here and try to derive the different other parameters associated with the hybrid model. Now the next parameter we want to derive is the overall voltage gain. Now we know that the overall voltage gain is, okay, so this is the overall voltage gain. So if we connect the external voltage source with the equivalent, suppose this is your 1 minute. Okay, so this is your H parameter model. So in this H parameter model you can see this is the source resistance, okay, and this is the source voltage. So if you connect this, up to now we have derived the voltage gain, that is the input voltage, as input voltage is considered is this, and the output voltage is the same, okay, V0. We have calculated V0 divided by V1, and that voltage gain is written as AV. Okay, but when we calculate the external voltage source along with the series resistance, then the voltage gain V0 divided by Vs, this is called the overall voltage gain. Okay, so this is the diagram, this is the actual diagram. Whenever we calculated V0 divided by V1, this is called as AV, simply the voltage gain, and whenever we calculated V0 divided by Vs, this is called the overall voltage gain. Okay, overall voltage gain or AVS, overall voltage gain. So now we will try to derive the overall voltage gain. So in the case of the calculation of the overall voltage gain, as I have said that overall voltage gain is represented by V0 divided by Vs. Okay, now this can also be written as V0 divided by V1. And what is V1? I have showed you what do you mean by this V1. V1 is this voltage, this voltage is V1, whatever voltage is actually falling onto the input section of the transistor, that is the V1. So V0 divided by V1 into V1 divided by Vs, you can written the overall voltage gain expression as this. Now as I have said that this is your voltage source Vs, and this is your series resistance Rs, and the input resistance we have also calculated the equivalent input resistance. Okay, so this is the equivalent input resistance considering all the parameter. So the input resistance can be drawn like this. Okay, so this is the minimized diagram. So voltage source with a series resistance with a input resistance, if you connect this externally, okay, along with the model, so this can be written as V0 divided by V1, this can be written as AV, simply the voltage gain, and this V1, the voltage falling across this input resistance is V1. So this V1 can be written as the voltage division rule. V1 is nothing but Vs into this Ri divided by Ri plus Rs, simply voltage division rule. So V1 divided by Vs is nothing but Ri divided by R1 plus Rs. So Ri divided by Ri plus Rs. So this is the overall voltage gain. Now this voltage gain, this overall voltage gain, that is represented by AVS, is always less than AV. Okay, so this way, if in the question it is asked you to calculate the overall voltage gain, so this is the expression for the overall voltage gain. Also in a similar fashion we will try to calculate the overall current gain. Previously we have calculated also the current gain. Okay, so in the case of the current gain, likewise this is the voltage source. This source transformation has been taken place if we want to calculate the current gain. So this way we can transform this. So this is a current source along with a parallel series resistance. This current is represented by Is, and this is your overall input resistance calculated considering all the parameter. So this is the current I1. Okay, so the overall current gain, I'm just writing down the overall current gain is equal to, okay, the same way, in the same way we have calculated the overall voltage gain I0 divided by Is, and it can also be written as I0 divided by I1 into I1 divided by Is. Now I0 divided by I1, this can also be written as current gain simply, and I1 divided by Is. So this is your Is and this is your I1. So I1 is nothing but just the current division rule. So Rs divided by Ri plus Rs into Is. So this is the expression for I1. So I1 divided by Is is nothing but Rs divided by Ri plus Rs. Okay, so this is the expression for the overall current gain. So overall current gain is likewise in the case of the voltage gain. So this is your AI. So the overall current gain is always less than the current gain, simply the current gain. So this is also always less than the AI. So this is the overall voltage gain and the overall current gain expression. So next, the last parameter we want to calculate is output resistance. Now in the calculation of the output resistance, what we want to do here is that simply, 1 minute, I am just drawing the hybrid model. This is your Rs, this is your HI, sorry, this is a dependent voltage source, plus minus, okay, this is your Rs, this is your voltage falling V1, okay, this is the current I1, this is the resistance Hi, and in that side there is also a dependent current source like this. This current source is Hf into I1. Next there is a resistance. This resistance is 1 upon H0. And now there is a trick. We are just want to calculate the output resistance. Okay, so for that purpose we remove the load resistance. We are looking the output resistance from here, R0. Okay, this is your R0. So likewise in the network theorem, just whenever we want to calculate the output resistance, we just remove the load and we calculate, connect a DC voltage source and short circuit the other independent sources. So there is a voltage and current is flowing through his I. So this is the procedure of the network theorem. Likewise in the network theorem, whenever you calculate the output resistance, this is the procedure. Okay, so we connect a arbitrary voltage source here, okay, and current flowing through is I, and the output resistance can be written as V divided by I, looking from that terminal. So this is the way we can calculate in our network theorem. Now this current I is the summation of these two current, this current plus a current flowing through this current is suppose I dash. So I equal to nothing but I dash plus Hf I1. Okay, this I current is going into these two branches, one branch, two branch. Okay, this resistance is 1 naught, 1 divided by H naught. Okay. So this I prime is nothing but, therefore there is a voltage V, so V divided by 1 divided by H naught. So I prime equal to V divided by 1 divided by H naught plus HF I1. Okay, so this is nothing but H naught V plus HF I1. Okay, so next we want to go to the input loop and try to find out the value of I, or whatever maybe we want to replace. We want to calculate the V divided by I. So first we will calculate the I1 in terms of the voltage. Okay, so go to the input loop. So there is a like this. Okay, so if we just make a KVL in this loop, this is HR V2. Okay, now V2 is the output voltage, so here the output voltage is V, so we can consider as HRV. So this is your HRV. So I am just writing down the KVL. So KVL is minus I1 into RS, this is, and this is minus I1 into HI plus, minus HR into V, this is plus to minus, that's why it is negative, HR into V equal to 0. From there you calculate the I1. So I1 is nothing but minus HRV divided by HI plus RS. Okay, so this is the value of RS, this is the value of I1. Now we want to replace the value of I1 here with this value. Okay, so you want to replace this I1 value here. So I am just writing I equal to, you can see I equal to H naught V, here it is H naught V plus HF, and actually it is negative, so I am just writing negative HF, and it is HRV divided by HRV divided by HI plus RS, HI plus RS. Okay, so this is the case. So from there you can easily calculate the value of R naught. Value of R naught, I said that V of I. So this is the procedure. We remove the load and connect a arbitrary voltage source, and whatever the value of current is flowing, so voltage divided by current, that is your output resistance. Looking back from this terminal, so HI divided by RS, HI plus RS, H naught, after the simplification, HI plus RS minus HF into HI. Okay, so this is the value of the output resistance. So hope you got that. So this is the all the parameter that we have derived associated with the H parameter, general H parameter model. So we have derived the input resistance, we have derived the voltage gain, we have derived the current gain, we have derived the overall voltage gain, also we have derived the overall current gain, and then lastly we have derived the output resistance. Okay, so these are the all parameter associated with this hybrid model. So next we will just consider the hybrid model for the CE configuration. Now if we just for the, I'm just not writing all this, I am just writing the CE configuration. So in the case of the CE configuration of the common emitter configuration, all the parameter associated with it, suppose there is a parameter HI, so in the case of the common emitter it is replaced by HIE. So there is a parameter HR, so that will be replaced by HRE. There is a parameter HF, that will be replaced by HFE. there is a parameter HO that will be replaced by HOE. So in the case of the common emitter, the H parameter is written by this. Okay, now I'm just drawing the model like this, H parameter model. So there is a resistance, there is a voltage source here, okay, there is a current source here, and there is a resistance here. So this is your VCE, collector terminal, base terminal, and this is your emitter terminal. This is your emitter terminal, which is common. Okay, so this voltage is VB. So this is the voltage source dependent, and this is represented by HIE, like this, HIE, and this is represented by HRE into VCE. Okay, so this is HRE into VCE, and this is nothing but HFE into IB. Okay, and 1 minute. And this is your C. Okay, output voltage. So and this is HOE. Okay, so this is the all the parameter that the H parameter, this is the all the H parameter, and in the case of the common emitter amplifier or the common emitter configuration, I have replaced all the parameter with an E, extra E, that is represented the common emitter. Now if I am just writing the input side and the output side equation for the case of this common emitter, okay, then it is input section. After applying the KVL, so VB is nothing but HIE into IB, current flowing through is IB. So HIE into IB, HRE into VC, HRE into VC. This is the input section KVL. So VB is nothing but HIE into IB plus HRE into VC, and the output section IC. This is current IC that is flowing through. So IC is nothing but summation of these two current. Okay, so IC is HFE IB plus HOE into VC. HOE has a unit of, I have said that HOE is actually 1 mho, that means 1 divided by ohm, and this is the voltage unit, volts of volt divided by resistance. So this is the actually the current. Okay, so that's why it is written like this. So this is the parameter different, this is the two different parameters, two different equation associated with this. Now here if we consider here the two terms, you can see that the VCE, okay, VCE is the reverse bias voltage across the output terminal. So this is the reverse bias voltage. So VCE is associated with the two parameter. You first look that the VCE is associated with this HRE and VCE is also associated with the HOE. Now this reverse bias voltage is actually responsible for the early effect. Okay, now if we just ignore the early effect, then we can ignore this HRE and HOE. In the question it is said to you that you can ignore the early effect, then you can ignore this HRE and HOE, these two parameter. Now if you just can ignore these two, then your IC divided by IB, this is your beta, and here in this case from this equation this is your HFE. Okay, so beta is nothing but your HFE. So this is the one thing associated with this if we just ignore the early effect of this transistor. Now if we ignore the early effect, now the model is similar to your T model that you will see in a moment. Okay, so this term is again repeating that this voltage is the output section voltage, and this output section voltage is nothing but the reverse bias voltage across the transistor. Now the reverse bias voltage is responsible for your early effect. Okay, reverse bias voltage is responsible for early effect. Now in the transistor, if we just ignore the early effect, okay, if we ignore the early effect, then as these two voltages associated with these two parameter, that means HRE and HOE, then we can ignore these two, hold these two term. Actually in the question many times it has been said that you can ignore the early effect. So it can ignore the early effect means you can actually ignore these two terms. So that's why this is important. I am again repeating this, and this is also, you can say that beta equal to HFE. This is very obvious from this equation, and if you just ignore the early effect, then your HRE and HRE and HOE can be ignored. These two terms can be ignored. Now if you ignore these two terms, then the circuit will look like very similar to your previous model. Okay, so there will be no dependent voltage source here, and there will be a dependent current source here, but there will be no HOE. Okay, but there will be no HOE. So this is your HFE into IB, this is your HIE, okay, and this is your VBE, this is your current flowing through is your IB, and there may be your load resistance connected across this voltage is your VCE, and load resistance may be connected across it. Okay, so this model is very much similar to your previous model. Now from there, if you want to calculate the current gain, suppose if you want to calculate the current gain, previously equation for the current gain is HF divided by 1 plus H naught into RL. Okay, so from there, if we just suppose this is your HFE divided by 1 plus HOE into RL. Now in this equation I am just here considering HOE, but here you can ignore the HOE if it is said that you can ignore the early effect. So in the question it can be said that if you can ignore the early effect, then you can readily ignore this term. And one more thing, you can ignore this HOE if and only if HOE can be ignored if you ignore the early effect. HOE can be ignored if you ignore the early effect, and HOE also can be ignored if HOE into RL, okay, HOE into RL less than 0.1. If this condition is satisfied or written in the question, then you can ignore this. So that means 1 plus 0.1, so you can 10 times lower, so you can actually ignore this term. So your AI is nothing but minus of HFE. Okay, so in this two way you can ignore, consider or ignore the early effect, then you can readily ignore this HOE. And if it is not said that in your question that you cannot ignore the early effect, then it has been said that HOE into RL is less than 0.1. So if it is less than 0.1, then you can readily ignore that. So in that two case, AI will be nothing but your minus HFE. Okay, next the input resistance. So input resistance is, your expression for the input resistance is HI plus HR AI into RL. Now ignoring the early effect, the same way, if you can ignore the early effect, so your input resistance is nothing but your HI. So this is your second, this is your first. Okay, and voltage gain. So in the case of the voltage gain expression, AI into RL divided by RI. So AI is nothing but minus HFE into RL divided by HIE. Okay, this is the expression for your voltage gain. Next is your overall voltage gain. So the overall voltage gain AVS is AV into RI divided by RI plus RS. Your AV into HI divided by HI plus RS. So in this way you can calculate by just approximating all these H parameter. Okay, so in this way you can calculate. So this is all about a small introduction of the H parameter model. So the summary is, till now we have discussed the BJT amplifier as a two-port network. Okay, so as we consider the BJT amplifier as a two-port network, then in the two-port network concept we use the H parameter model. So in the H parameter model we use the two equation of the H parameter model. So V1 equal to H11 I1, H12 V2, and I2 equal to H21 I1 plus H22 V2. And starting from this equation we have derived all these parameter, and we have also tried to draw the equivalent H parameter model, and we have also calculate the different, that means the input resistance, output resistance, voltage gain, current gain, overall voltage gain, overall current gain. Okay, like this, all these parameter, and then we will ignore the early effect. See how the ignoring the early effect affects the H parameter. So if we just ignore the early effect, then we can see the model is actually simplified very much, and your HI is this HI. If we just compare the HI with the previous model, then your this HI is nothing but your beta RE. Okay, in your previous model. So in your previous model I have said that what is beta RE. So if you just compare this model with that model, then you can easily see that this is nothing but your beta RE. So ignoring the early effect is the most important thing here. And if you just ignore the early effect, then your HOE and another parameter HRE, okay, HOE and HRE can be set to be 0, because these two parameter is associated with VC, and VC is only responsible for your early effect. Okay, so that's why whenever in the question it has been written, you carefully see the term, that whether it in the question it has been said to you to ignore the early effect or not. If it is said to ignore the early effect, then you easily minimize the H parameter like in this way, just by ignoring these two terms, and your H parameter will be simplified to a very good figure. Okay, so this is a very good figure, likewise in your previous model. So this is the all about the H parameter, and from the next class we will discuss more and try to solve some problem regarding this H parameter. Thank you.